Hi, this is Professor V.K. Patil. I welcome you to my video classes on basic electronics. In my last class, we have discussed about the comparator, which is one of the important application of the operational amplifier. And in comparator, remember that we use the open loop configuration, not a closed loop. Whereas in all other applications, we have used the op-amp in closed loop configuration. Today we will discuss about some important op-amp parameters. Usually when I wish to use the op-amp for the particular application, I need to take care of all these parameters. The important parameters what we are going to discuss are, the first one is input and output offset voltage. When you purchase the op-amp and if you see the data sheet of particular op-amp, all these parameters are specified on the data sheet. So what is this input and output offset voltage of a op-amp? Let us consider the op-amp. So op-amp, it has non-inverting terminal, inverting terminal, bias voltages, let us say these are plus VCC, minus VCC, output voltage is V0. If the input to the inverting as well as non-inverting terminal are 0, it means that if the non-inverting terminal as well as inverting terminal is grounded, output voltage, what it is expected, output voltage, so it must be a 0. This is what the expected. Is it right? So reason is that output voltage, which is equal to A into VD. So voltage at non-inverting terminal, voltage at inverting terminal, both are 0. 0 minus 0, I will get VD, which is equal to 0. Hence I will get this as 0. Is it right? But this is not happening with a practical op-amps. If I ground the non-inverting terminal as well as inverting terminal, I will get some output voltage, and that output voltage we'll call it as the output offset voltage. What is the definition of output offset voltage? When we apply the 0 input voltage to the inverting as well as non-inverting terminal of a op-amp, I will get some output voltage which is not 0, and that output voltage we call it as the output offset voltage. Then what is the input offset voltage? Now I need to compensate this output offset voltage, right? So what do you mean by compensate? I need to make it 0. How to make it 0? To make it 0, I need to apply some differential input voltage at the input terminal. For example, let us say this is something 0.5 millivolts. I want to cancel it, and to cancel that I need to apply some voltage, differential voltage in between these input terminals, and the voltage which is connected at the input of the op-amp to compensate output offset voltage is known as input offset voltage. So when I apply the 0 input voltage to the op-amp, it is expected that output voltage must be a 0, but this is not happening in a practical op-amps. I will get some certain output voltage even though inputs are 0, and that voltage we call it as the output offset voltage. And what is the input offset voltage? The input offset voltage, it is the voltage which is applied at the input of the op-amp to make this offset voltage 0. That is nothing but the input offset voltage. So these are the two important parameters related to the operational amplifier. The next important parameters related to the op-amps are offset and bias current. Let us consider the op-amp in open loop configuration. This is output, inputs are V1 and V2. So these are the biasing voltages, plus VCC and minus VCC. Till now what we have considered are ideal op-amp, and we know that the current entering into the ideal op-amp is 0, but practically some current is flowing inside the op-amp. When biasing voltages are applied, some current it starts flowing inside the op-amp through non-inverting as well as inverting terminal. Let us say IB1, it is the current which is flowing inside the op-amp through non-inverting terminal. IB2, it is the current which is flowing inside the op-amp through the inverting terminal when biasing voltages are applied. I have not applied input, but I have applied the biasing voltage. Then the bias current, that is input bias current, can be defined as the average of these two, that is nothing but IB1 plus IB2 divided by 2. This is nothing but the input bias current. Getting my point? When we apply the biasing voltage to the op-amp, IB1 and IB2, these are the currents which are flowing inside the op-amp through the non-inverting and inverting terminal respectively. Then average of these, the current which are entering into the op-amp is known as input bias current. What is input offset current? So input offset current is the difference between these two, IB1 minus IB2. The difference between the IB1 and IB2 is known as input offset current. So these two more important parameters are common mode rejection ratio and slew rate. Let us first discuss common mode rejection ratio, most commonly abbreviated as CMRR, common mode rejection ratio. Let us assume the op-amp. When I apply a common mode signal, so this is the signal which is known as common mode signal, VCM. That is what the signal is common to the non-inverting as well as inverting terminal, then which is equal to ACM, where ACM is common mode gain multiplied by common mode input. The common mode rejection ratio is defined as CMRR is defined as the differential gain divided by common mode gain, and it is expected that so this common mode rejection ratio, it should be as minimum as possible for the op-amp. Basically, this common mode rejection ratio, it tells the ability of op-amp to suppress the common mode signals. Usually, suppose if the op-amp is used in a noisy environment, the noise which is inputted at the non-inverting terminal, same kind of noise it is inputted to the inverting terminal. Hence at the output, so this noise must be suppressed, right? So when the same quantity is applied as the input to the non-inverting and inverting terminal, they get suppressed at the output. And this common mode rejection ratio basically defines the ability of op-amp to suppress the common mode signals, and it can be defined as the differential gain divided by common mode gain. Common mode gain is nothing but common mode signal is applied. The differential gain, the gain of the op-amp when the two different inputs are applied, and the gain it becomes AD, differential gain, multiplied by VD, which is nothing but differential input. So this is what the common mode rejection ratio. Another important parameter is slew rate. The slew rate basically defines how the op-amp responds to the input. Basically, it gives you the idea about how fast the op-amp it responds to the input. Right. So the unit for this slew rate is voltages per microseconds. Voltages per microseconds. For this reason, let us assume again the op-amp. So suppose if we apply some input and output is something square, or expected output is something square. Is it right? So the slew rate, it defines how fast the output it changes from 0 to its maximum value, and the slope of this particular graph, that is nothing but the slew rate. And slew rate, it should be the as maximum as possible. Slew rate Basically, it defines how fast the output varies from its lowest value to its highest value, and it is expected that slew rate it must be as high as possible. These are some of the important parameters related to the operational amplifier. Thank you. This is the end of module number 3. In this module number 3, we have discussed introduction to the op-amp. We have discussed the symbol model of an amplifier. Then we have discussed the open loop configuration. In open loop configuration, we have discussed inverting amplifier, non-inverting amplifier, differential amplifier. We have discussed the region of operation of an amplifier. In the region, we have negative saturation region, linear region, then positive saturation region. Next to that, we have discussed the different applications in a closed loop configuration. Basically, in closed loop configuration, I can control the gain of a circuit, whereas in open loop configuration, I cannot control it. The gain, it is the fixed one, which is in the range of 10⁵ to 10⁶. Also, we have discussed the characteristics of the ideal op-amp. Then we have discussed the applications like summing amplifier, scaling amplifier, subtractor, differential amplifier in closed loop configuration, inverting amplifier in closed loop configuration, non-inverting amplifier in closed loop configuration. Then we have discussed integrator, differentiator, and the last application what we have discussed is comparator. Next to that, we have discussed the different important parameters related to the op-amp. So while choosing the op-amp, we need to take care about this all important parameters. Thank you. We will see some other module in next class.